In the previous module, we introduced an important statistical tool, the hypothesis test. This module will provide us some additional concepts underlying the hypothesis testing framework. I'm going to begin with one of the examples from our homework, namely the problem where Willard Longcor was rolling a whole bunch of dice. You should know that this really did happen. Willard Longcor really did roll precision-made and inexpensive dice many, many times. Some background explanation is in order. If you look at inexpensive dice, the spots, the numbers on the dice are formed. There are indentations in the dice. They're painted of a contrasting color. These are very, very cheap to produce. You can get packages of 100 of them for a few bucks from Amazon. Notice how they're constructed. The 1 is opposite the 6, the 2 is opposite the 5, the 3 is opposite the 4. And since the 6th side has 6 holes in it, and the one side opposite it only has 1 hole in it, the one side is heavier. And so that die is not exactly balanced. The precision-made dice deal with this. They fill those holes in with material of the same density but a contrasting color, then smooth things off so you've got a near perfect cube. They're very well balanced, but they're also pretty expensive, several dollars a piece. So back around 1970, Fred Mosteller is chair of the statistics department at Harvard. And one day, out of the blue, he gets a letter from someone in Waukegan, Illinois, a suburb of Chicago, by the name of Willard Longcor, wanting to know whether Harvard would be interested in some actual results from real live die rolls. And Mosteller says, well, I guess so. And Longcor proceeds over the course of many, many months to start rolling dice. He builds a special casino model die rolling table, felted table, walls, cushions to use casino parlance, around the table, and when he rolls the die he makes sure it bounces off at least 2 of these cushions to ensure proper rolling randomness here. Each die is replaced after 20,000 rolls to reduce impact of wear and tear on the die. And he records how many even and odd numbers were obtained in each batch. And after each batch of 20,000 rolls, he sends the results into Harvard. It's a hypothesis test. Are the dice fair or not? A fair die will have a true population proportion of heads of 50%, and if it's not fair, alternative hypothesis, not 50%. Once we've defined and quantified hypotheses, we go out and collect our data. Here are the data for the 2 million rolls of the precision-made dice. They came up evens 50.045% of the time. We compute a test statistic and p-value. Our test statistic is observed minus expected over standard deviation. We observe 50.045% heads. Standard deviation is p, 1 minus p over n. The 1.27 means that what we got is 1.27 standard deviations away from what we expected. It's easiest to look up the lower tail probability, throw the negative sign on. This area down here is 0.102. This area up here will be the same, so the overall shaded area is 20%. That's our p-value. Our statistical decision with a p-value bigger than 0.05, do we reject or not reject the null hypothesis? We're saying this is a relatively common occurrence, nothing too unusual here. There's no reason to reject that null hypothesis. And again, we don't care about hypotheses, we care about the dice. We need to make an applied decision. In this case, by not rejecting, we're saying there's not enough evidence that the die is biased. We can do similar computations for the inexpensive dice. Now the 50.725% that we observed compared with expected. Longcor only did this one 1,160,000 times, but we're 15.6 standard deviations away. You really don't even need an Excel function for that. Probability out that far is essentially 0 for all practical purposes. We reject the null hypothesis. There is enough evidence that the die is biased. And so we walk through the basic computations for Willard Longcor's experiment. In the next video, we'll look at some implications as to what this means in practice.